problem involving the ideal transformer. There are a couple of things that we'll want to keep in mind. First, first of all, we have our model of the ideal transformer. The N1, N2 is the turns ratio, and we're going to use the dot convention, similar to mutual inductances. It's a little bit different, and I'll explain as I go what I've found to be the easiest way to keep this stuff in mind. Essentially, what we're going to do, though, is these problems are going to be typically very simple as far as the transformer is concerned, because what we're going to do is use reflection to simplify the circuit. Essentially, we can remove the an ideal transformer from the circuit altogether. So we're going to define N as N2 over N1, and that will be the turn ratio. And then to use reflection, if the dots are both at the top, or I guess both at the bottom, then you can use these two equations right here to relate currents and voltages. So any node voltage or voltage across a component would obey this rule, and this is left to right as well, and I the same way. And the impedances, this equation will work for an ideal transformer regardless of the dot configuration. If the dots are opposite each other, then you'll put a negative sign in front of both of those answers. It's really that simple. So let's tackle this problem. I chose it because it has both kinds of configurations, and it's got a couple of I guess you could call them tricky parts to it, but they're really not that tricky once we get into them. Okay, so the first thing that we'll do is we'll take this transformer here. I'll put a little blue circle around it so we know what we're working with, and we'll figure out all the calculations that we need for this particular one. So for this N blue, N, the turn ratio, is going to be equal N2 over N1. That's 1/2. Okay, and these are opposing, so we'll use the negative. So V1 equals minus V2 over N, and I1 equals minus N times I2. And then for the other one, give this a red circle, I guess. We're going to look at the turn ratio as N1 to N2. So that's going to be 2. So N would equal 2 here. And because of the dot configuration, we get equations that look like this. And the question is asking for us to find the voltage across this resistor. So what seems easiest to me would be to use reflection and reflect all of these components over to this mesh, and then reflect all of these components into that same mesh as well. Okay, so the next thing that I'll do is I'll draw the circuit. Our new circuit will look something like this. That's our first component on the left, and we'll just remove the ideal transformer altogether. Okay, and I can remove this ideal transformer altogether. And just for simplicity, I'm going to draw this like this. If that's at all confusing, convince yourself that if we just took this node and connected them, took these three and connected them, and these two and connected them, that it would look like this. Okay, and now we need to fill in the values. Well, these two values aren't changing because we're not using reflection here. Okay, so this is just minus J6, and this is 6 ohms. We're still looking for V0. And we'll start over here on the left. So we want to know, we have the voltage on the left, and we want to know what would the voltage on the right be. So we use our equations here. We know this one, and we want to figure out the one on the right. So what we'll do is we'll take we'll multiply this side by negative n. Okay, so we get for our V2 equals negative n, and we'll just plug in numbers here actually. Negative n, which is negative 1/2, times 32 angle 0. Okay, and that equals minus 16 angle 0. So that tells us then that the polarity flips when we reflect this power over this power source. Okay, so that's going to be 16 angle 0. So I just, instead of putting the negative sign, I just flipped the battery. Okay, the resistor, I use my general equation here, which is that Z1 equals Z2 over n squared. And so I want to find Z2, so it's going to be Z1 n squared. Okay, so Z1 is 4. Let me just explicitly say what we're doing here. Z for the resistor is going to equal 4 times n squared times 1/2 squared. So that's 1/4 times 4. This just equals 1. Okay, and then the capacitor equals minus J8 times 1/2 squared, and that simply equals minus J2. Okay, so this is 1, and this is minus J2. And now we look at the last set of equations. So we have to use these equations right here for this one. I want to reflect this resistor up, and I know if you kind of tilt your head to the left, you can imagine that this is Z1, and we want to find out what Z2 is. So again, it's going to be Z1 times n squared. So that's going to be ZR equals Z1, we'll just put in the number, 6 ohms, times 2 squared. Okay, and that equals 24. So this is 24 ohms. And then the inductor is finally, if you just plug that in, you'll find that the inductor is J12 times 2 squared. So that's 48. Okay, and that's basically it. This is now solvable using any method that we've used before. If I want to find V0, well, I'll probably just find the current. I can do that really quickly, by taking the voltage source and dividing it by the total impedance. Keeping in mind that the current, according to the battery, is traveling this way. So V0 is going to actually equal the negative of the voltage that we calculate across the resistor. So let's calculate that really quickly. So we have 16 angle 0. We're looking for I. Okay, it equals the voltage divided by the impedance. And if you add those impedances up, you should come up with 31 plus J38. Okay, and when you divide that out, you will get a number like this. (206 minus 0.25 to J, and that's the current. Now we want to figure out what the voltage is across the resistor, so we're going to take the negative, because remember we're not following the sign convention with V0 here. So V0 equals the negative of 0.206 minus J 0.252 times 6. And let me just, I'm just doing it on my calculator really quickly to verify that this is right. Indeed it is. What you'll come up with, and if you didn't put the negative sign you won't get it right, what you should get is that V0 equals minus 1, oops, sorry, yes, I'm sorry, minus 1.95, no, 1.95 angle 129.26. Okay, and that's how you solve those kinds of problems.